When we dissolve a solute in a solvent, its properties change. Today we will discuss some important properties of solutions quantitatively. Hello and welcome to PhysChem Basics. Our topic today, classical solutions. How do solvents and solutions differ? Before we start with the actual topic, a note about the concentration of solutions. If we dissolve 1 mole of sugar in 1 kilogram of water, we have a solution of molality 1. There are 1 mole of dissolved particles in 1 kilogram of water. The so-called colligative properties depend on this very number of dissolved particles, no matter what nature of the particle. So when we prepare an electrolyte solution, a solution of a salt, we have to take into account that the salt dissociates. Half a mole of table salt will dissociate in solution to 1 mole of particles, cations and anions. The number of dissolved particles is twice the amount of salt used. The relation between actually dissolved particles and originally dissolved amount of substance is called Van 't Hoff factor I. In order to quantify the number of particles in the specification of concentration, the so-called osmolarity and osmolality were introduced. The table salt solution, the saline, has a molality of 0.5 but an osmolality of 1. The solution therefore contains as many dissolved particles as the sugar solution discussed above. The two solutions are equal in osmolality. The two solutions are isotonic. Accordingly, we get the osmolarity from the molarity by multiplying by the Van 't Hoff factor. A simple solution contains two components, solvent A and solute B. Depending on how the interactions between these components are, a distinction is made between ideal and non-ideal solutions. If we mix two chemically very similar components, the enthalpy of the mixture corresponds exactly to the enthalpy of the starting materials. There is no enthalpy of mixing, no heat of mixing. We are talking about ideal solutions. The so-called Fleury-Huggins coefficient Chi equals 0. However, if the two components are energetically appealing or unappealing, heat is released or heat is consumed when mixing. Non-ideal solutions may thus show a negative or positive Fleury-Huggins coefficient. Fleury and Huggins thermodynamically analyzed the mixture of two components. Depending on the magnitude of the intra-component and the intercomponent interactions, the mixture is either ideal, exothermic or endothermic, expressed by the Fleury-Huggins coefficient Chi. The theory derives equations that can be used to calculate enthalpy, entropy and free energy of mixing. The following explanations apply to ideal solutions. That is, solutions in which intra-component and intercomponent interactions are similar. Chi is 0. In this PT phase diagram we see the vapor pressure curve, melting pressure curve and the triple point of a solvent marked in red. The corresponding curves for a solution are drawn in green. According to Raoult's first law, the vapor pressure of a solution is always lower than the vapor pressure of the solvent. A liquid boils when its vapor pressure is equal to the external pressure. However, a solution has a lower vapor pressure at the same temperature, expressed by Raoult's first law. Thus, in order to boil a solution, we have to further raise the temperature. The solution exerts a higher boiling point than the pure solvent, expressed by this equation. K sub Eb is the ebullioscopic constant, a characteristic of every solvent. For water, this constant is approximately 0.5 kelvins kilogram per mole. This means that any solution of osmolality 1, like the sugar or salt solutions in our examples, will have a boiling point of 100.5 centigrade. A solvent freezes when liquid and solid have the same vapor pressure. That is, at the temperature where the vapor pressure curve and the sublimation pressure curve intersect. In the case of a solution, this intersection is shifted to lower temperatures. There is a so-called freezing point depression of a solution compared to the solvent, expressed by this equation, also known as Raoult's second law. The constant K sub Cr is the cryoscopic constant, another characteristic for every solvent. For water, the cryoscopic constant is 1.86 kelvins kilogram per mole. This means that any solution with osmolality 1, like the isotonic sugar and salt solution in our examples, both freeze at negative 1.86 centigrade. The solution always has a lower vapor pressure than the solvent, which means that the solution is more stable than the solvent. If we separate the solution and the solvent by a semi-permeable membrane, then solvent molecules will voluntarily move into the more concentrated solution. This will create an additional pressure in this solution. This transport process continues until the pressure in the solution has become so high that the stability in both phases is identical again. The additional pressure which builds up in the more concentrated solution is called the osmotic pressure. According to Van 't Hoff, we can calculate it from osmolarity, the gas constant, and temperature. This commercially available saline solution with an osmolarity of 0.3 moles per kilogram shows an osmotic pressure of 0.76 megapascals. This is exactly the osmotic pressure of human blood, so these solutions are used in intravenous therapy. Since many biological cell membranes are semi-permeable, osmotic pressure plays a major role in biology. Body fluids should be isotonic, otherwise cells could be damaged. In hypertonic media, cells may lose water very quickly and die. This also means that no regular microorganism will survive in a concentrated solution. That's why the Dead Sea got its name. Osmosis can also be reversed. By applying a sufficiently high pressure, a solution can be kind of ultrafiltrated and turned into the solvent. That's how seawater is treated in desalination plants. Osmotic pressure, freezing point depression, and boiling point elevation are colligative properties, the magnitude of which depend only on the number of dissolved particles, but not on their chemical nature. Therefore, these properties are well suited to determine molar masses of dissolved compounds. For example, osmometry is used to determine the molecular masses of proteins and polymers. Let's summarize. The thermodynamics of mixing can be described according to the theory of Flory and Huggins. With so-called ideal solutions, there is no heat of mixing and the Flory-Huggins coefficient chi equals 0. The solution always shows a lower vapor pressure than the pure solvent, which can be calculated with Raoult's first law. A solution has both a higher boiling point and a lower freezing point than the pure solvent. The properties mentioned are colligative, which means only the number of dissolved particles is decisive, not the chemical nature of the solute. Osmotic pressure is another colligative property. It can be calculated using Van 't Hoff's equation, and it especially plays an important role in biology. More information about the topic you'll find in the book and in the lecture. Thanks for watching.